This is the 12th video in a series covering complex analysis. And today we're going to look at complex integration up to Cauchy's theorem. But before we do that, I'd like to recall a result that classifies analytic functions, as this will be something that we use today. And that says that if we break a function f into its real and imaginary part, so in other words, we write f as u plus iv, this function is analytic if and only if it satisfies the so-called Cauchy-Riemann equations. And I've left off a little bit of a hypothesis here having to do with its analytic on a domain, which is a simply connected open subset of C. Okay. And also the Cauchy-Riemann equations are defined by partial u with respect to x equals partial v with respect to y, and the partial of u with respect to y is equal to minus the partial of v with respect to x. So before we get started on our complex integration, I'd like to look at a complex version of the Cauchy-Riemann equations. And so let's do that as follows. Let's take the partial of f with respect to x, and notice that in this case, we get the partial of u with respect to x plus I times the partial of v with respect to x. But now using this formula right here, or these equations right here, we can make some replacements. Equals the partial of v with respect to y minus I times the partial of u with respect to y. But then we can factor out a minus I, but factoring out a minus I is like factoring a 1 over I, because 1 over I is minus I, and that gives us 1 over I times the partial of u with respect to y plus I times the partial of v with respect to y. But let's notice that's 1 over I times the partial of f with respect to y. And so going from here, this partial of f with respect to x down to 1 over I times the partial of f with respect to y is sometimes known as the complex form of the Cauchy-Riemann equations. But notice that it's a single equation given that we have the u and v components built into it. And I'd like to point out that if f is analytic, then both of these are equal to what we would generally call f prime of z, which is the derivative of f with respect to the entire complex variable z. Okay, so we'll keep this in mind as we move forward today. Okay, so now we're ready to start looking at complex integration, and we're going to do this via a couple of examples first before we start proving results. I'd like to point out that integrals in the complex plane are necessarily line integrals. This is maybe a little bit less careful than it could be written. What I really mean is single integrals in the complex plane are line integrals. But that means that we've got multiple paths. If you think about two numbers in the complex plane, let's call them maybe alpha and beta, there are most definitely infinitely many paths that can link alpha and beta. There's this straight line segment, and then maybe there's this curve like this. You could even have something crazy that curves around like this. All of those are paths that begin at alpha and end at beta. So it seems like before we dive into this, a complex integral will not just depend on the endpoints, but it will also depend on the path. So let's investigate that to see if it's true. And we'll do that via a couple of examples, like I said, before we look at some general results. So let's let gamma in this case be equal to the line segment from the origin to the point 1 plus I. So we can parameterize that pretty nicely as gamma of t is equal to 1 plus I times t. So notice when t is equal to 0, we're exactly at 0, the origin, and when t is equal to 1, we're exactly at 1 plus I. So this is parameterized over the unit interval. Okay, so let's say we have that, and then let's calculate the integral over gamma of z dz, like this. Okay, but let's recall that z is x plus iy, so that's going to be the integral over gamma of x plus iy. And then we'll take dz to be dx plus I dy. So we have dx plus I dy. But then we can use our parameterization to see what x and y are. So notice from this formula right here, we see that x of t is just equal to t, and y of t is also just equal to t. So that's nice. So that means that we can take this and plug in our parameterization to give us the integral from 0 to 1 of, let's see, 1 plus I times t. So that would be like our x plus iy. And then we'll have 1 plus I dt. So that'll be like our dx plus I dy term. Notice we can factor out a 1 plus I squared. So we have 1 plus I squared, and then the integral from 0 to 1 of t squared dt. But now we've just got a real integral. That's pretty easy to calculate. That ends up leaving us with 1 plus I squared over 2, which in fact simplifies to I. Okay, so that's the calculation. But what I'd like to point out, especially given this kind of penultimate step here, is that this looks like we had just forgotten that it was a line integral and applied the fundamental theorem of calculus. So let's say this would look like the integral from 0 to 1 plus I of z dz, and then we would take the antiderivative to give us z squared over 2 evaluated at 0 and 1 plus I, but that would give us 1 plus I squared over 2. So it seems like we get the same result if we had never even thought that we had to do a line integral in the first place, as if we worked through this carefully. Okay, before we maybe state and prove a result that in fact says we're able to do something like this, let's look at the integral of the same function with the same starting and ending points, but over a different path. So the second path we'll take is these two line segments that have been glued together. So we have the line segment from the origin to the number 1, I'll call that gamma 1. And then the line segment from 1 to 1 plus I, I'll call that gamma 2. And like I said before, we're going to integrate the same function over now those two line segments. So let's parameterize each of those. So we can write gamma 1 of t will just be t. And here we've got t is going between 0 and 1. Well, that's just because we're staying on the real axis, so that's pretty clear. And then gamma 2 of t will be equal to 1 plus I times t. And there we'll have t is going between 0 and 1 as well. So that takes us from here up to here. Okay, so that means that we can take this integral over gamma of z dz and break it into the integral over gamma 1 of z dz plus the integral over gamma 2 of z dz. But then each of those need to be broken up into the x plus iy times dx plus I dy format. Okay, so let's see this first one. That'll give us the integral from 0 to 1 of, well, z, that's x plus iy. But notice in gamma 1, we have x is equal to t and y is equal to 0. So that's just going to give us t. And then dz, that's, like I said, dx plus I dy, but dy will be equal to 0 for the same sort of reason, and dt will just be, or dx will just be dt. So that's what we get for that first integral. Now let's see what we have for the second one. So again, that's the integral from 0 to 1. But now z will look like this. So we have 1 plus I times t. And then we have our I dy. But our I dy here will be exactly I dt. So here we have I dt. Now, before we make our calculation, notice that we can rewrite this one a little bit by distributing this I through. So this, in fact, gives us the integral from 0 to 1 of I minus t dt when all is said and done. Okay, now we're ready to finish this off pretty easily. So we can, in fact, combine these two things together, and the t dt will cancel, leaving us just with the integral from 0 to 1 of I dt, which will just give us the number I. But let's recall that's exactly what we got before. So that doesn't prove that these complex integrals are independent of path, but that gives us some motivation that at least this complex complex integral only depends on the inputs, the endpoints, I should say. So in this case, the origin and 1 plus I. Okay, so let's get rid of this, and then we're going to prove a result that tells us when we are able to do complex integration using the same sort of strategy of finding an antiderivative like we did for real integration. So now we're ready for something called the fundamental theorem of calculus for analytic functions. There's quite a bit of a setup, but we'll go through it just one step at a time. So let's suppose that f is a continuous function on a domain D. Recall that being a domain means that you are an open set who is simply connected in the complex plane. And then capital F is analytic on D. So analytic means it satisfies these types of equations over here. And then also we have the derivative of capital F equals little f. Then for any path gamma from alpha to beta, we have the integral along that path of gamma of little f of z dz is equal to capital F evaluated at beta minus capital F evaluated at alpha. But since this is true for any path from alpha to beta, that motivates us to define the following integral, which is the integral from alpha to beta of f of z dz. And so this kind of extreme left and right hand side of what we have here looks like the fundamental theorem of calculus that you might see in like a calculus 1 type class. But the important thing here is that we've got this analytic thing playing the role of an antiderivative. And in fact, we've got a different word for it in complex analysis. This capital F is called a primitive of little f. So now let's see how the proof goes. And it's actually going to go pretty easily because we're going to use some results from multivariable calculus. So let's see. So since capital F is analytic, that tells us that the partial of f with respect to x is equal to 1 over I times the partial of f with respect to y, which is equal to f prime of z. So again, that's something that we did at the very beginning of this video. So now we can start with the right-hand side. This is going to be f of beta minus f of alpha. And notice that this is equal to the integral over gamma of the gradient of f dot dr. And so we'll go through all of these parts, but this is by the fundamental theorem of calculus for line integrals. So I'll just write line integral ftc, which is something that you would cover, like I said, in a multivariable calculus class. Okay, nice. So, but the gradient of f is exactly equal to the vector formed by the partial of f with respect to x and the partial of f with respect to y. And then dot dr is the standard notation from multivariable calculus for the vector made up of these infinitesimals dx dy. Okay, but now we can do that dot product and we'll get the line integral over gamma of the partial of f with respect to x dx plus the partial of f with respect to y dy, like that. But now let's notice that we can replace this partial of f with respect to x with f prime of z by the complex form of the Cauchy-Riemann equations, and we can replace this partial of f with respect to y with I times f prime of z by, again, the complex form of the Cauchy-Riemann equations. But that allows us to factor in f prime out, and we're left with the integral over gamma of f prime, but f prime is little f times dx plus I dy, but dx plus I dy is dz. And that finishes this proof. So let's get rid of this and we'll look at an example where this is not quite applicable. So now we're going to look at an example when the fundamental theorem of calculus for analytic functions does not apply. And that is the case when a function does not have an analytic primitive. So this is maybe the classic first type of example. And that is the integral over the unit circle. So that's everywhere where the modulus of z equals 1 of 1 over z dz. So notice that this thing has a primitive, that would be the log z. But if you recall from when we looked at the logarithm, the negative real axis, or really the non-positive real axis, was a place where we had to make a branch cut. So this log z was non-analytic on the non-positive real axis. And that includes part of this region right here. Okay, so that means we have to do this just using our old method of parametrizing the unit circle and thinking of this like a line integral. So let's do that. We can easily parameterize the unit circle with z equals e to the I theta. But then you can calculate that dz is equal to I times e to the I theta d theta. Now, if you want to run through this in rectangular form as like cosine theta plus I sine theta and then calculate dz with the dx plus I dy, you can do that, but you'll end up with the exact same thing here. Then I'd also like to point out that theta comes from the interval 0 to 2 pi, not including 2 pi. Okay, but that means that this integral is the same thing as the integral from 0 to 2 pi of, let's see, we have I e to the I theta d theta in the numerator over e to the I theta in the denominator. That comes from our dz over z. But notice that gives us I times the integral from 0 to 2 pi of d theta, which is just 2 pi times I. So just to reiterate what we had to do here, we had to use this method of parametrizing the line integral because this did not have an analytic primitive. Now we're going to look at this example again, but we're going to do a little bit of a hack of the fundamental theorem of calculus so that we can use it. So let's just look at the last example that we had and reiterate what the problem was, and then hack it so that we can use the fundamental theorem of calculus. So we're looking for the integral of 1 over z dz over the unit circle. But let's notice the primitive, or the complex antiderivative of 1 over z is the logarithm of z. We can take any branch here, but we'll take the standard branch or the principal branch. So that means the derivative with respect to z of log z is 1 over z, but log z is analytic on c minus the interval from minus infinity to 0. So that's the non-positive real axis. And so that means as we loop around our unit circle, we have a problem right here at the point -1, because that's clearly in the portion of the complex plane where this is not analytic. So what's our fix? Well, our fix is to maybe remove this single point from the line integral, and then use a limit to maybe patch it back together. Okay, so after removing this little bubble, now we can apply the fundamental theorem of calculus because we're in a region where this primitive is analytic. So that means we can write this as the integral from maybe a point that's just outside of this bubble but below. So that would be like of the form e to the I minus pi minus epsilon, keeping in mind that we're still on the unit circle and everything on the unit circle is of the form e to the I theta. Okay, so just to kind of reiterate what's happening here, that point would be like right here, just right before this thing. And then we would have at the top e to the I pi plus epsilon. And so that point would be right here above that bubble. Okay, but then since we're trying to patch this back together, we need to put a limit as epsilon goes to 0 from above in. And now we have 1 over z dz. So now, like I said before, we can use the fundamental theorem of calculus for analytic functions just to take the antiderivative or take the primitive and plug the two endpoints in. So that gives me the limit as epsilon goes to 0 from above of the log of z evaluated at e to the I pi minus epsilon and e to the I pi plus epsilon. And this should be minus pi. But now let's see what we get. That's going to give us the limit as epsilon goes to 0 from above. This gives us I pi plus epsilon, and this gives us another copy of I pi plus epsilon because the signs change after we do the subtraction. Notice the logarithm brings those exponents down. But now notice as epsilon goes to 0, those two guys go to 0, and we get 2 pi I, which is the same result that we had before. And so this is a nice trick to use the fundamental theorem of calculus by taking this limiting procedure when it in fact was not applicable. So this is something nice to keep in mind. Okay, so let's maybe get rid of this, and we're actually going to do this example one more time, but we're going to do it using some like kind of sketchy looking notation, which is pretty common in complex analysis. That's just an easy way of doing this careful thing quickly. We're going to do this one more time, but now we're going to use, like I said, some sketchy notation, but this is kind of well known to be a shorthand for what we just did. So let's say this is the same thing as the integral of 1 over z dz, where now we need a starting point and an ending point. And what we'll take for a starting point is the number -1, but -1, which is just below the imaginary axis. So we'll write that as -1 minus I times 0. So like I said, it's pretty sketchy, but this will work out. Then we'll have -1, but then just above the real axis. So that'll be -1 plus I times 0. But now on this region, which we actually view this via the limiting procedure that we did before, we can take the antiderivative and plug in the endpoints. So that's going to give us the log of -1 plus I times 0. And then minus the log of -1 minus I times 0. So let's recall that the complex logarithm is defined to be the natural log of the modulus. So the modulus of this is 1 plus I times the argument. But what's the argument of the log of -1 plus I times 0? Well, recall that that's just above the negative real axis. But being just above the negative real axis means it has an argument of pi. And then we're going to subtract from that, well, this thing, but that's going to be the natural log of the modulus again, which is -1, and then plus I times the argument. But now this is just below the negative real axis. And what's the argument of something just below the negative real axis? It is minus I pi, or minus pi. So in the end, when we add all of that up, we get 2 pi I once again. So this may seem like I said, kind of a dodgy way to do this, but this is really shorthand for what we did careful with the limits. This is kind of a standard trick which will shorten the number of steps that we have to do in the future. So let's get rid of this, and then we're going to prove a couple of results before we end the video. Now we're going to present a theorem which is pretty important for making estimates, which we'll kind of use a lot later to show a bunch of terms go to 0. So let's suppose that gamma is a piecewise smooth curve and f is continuous on gamma. Then we have the following inequality, which is essentially the triangle inequality for line integrals in the complex plane. That says the modulus of the integral over gamma of f of z dz is less than or equal to the integral over gamma of the modulus of f of z times the modulus of dz. And then furthermore, if the modulus of f is less than or equal to m on gamma and the length of gamma is L, this is less than or equal to m times L. Okay, so let's see how this goes. We'll start at the left-hand side and work all the way to the right-hand side. So we have the modulus of the integral over gamma of f of z dz is equal to, well, that's going to be the limit as capital N goes to infinity. Here we're just going to write down the definition of the integral using like the Riemann sum. So this is going to be the modulus of the sum as n goes from 1 to n of f evaluated at zn times delta z. Where of course there's kind of an undercurrent here that this Zn is really going to be gamma evaluated at Tn, where the Tn is like based off of a partition of whatever interval that we're having here. But I think this is kind of an okay way to do it here. Okay, but now we're just going to apply the triangle inequality because we have a finite sum here. And that's going to give us the limit as n goes to infinity of the integral from n up to n of the modulus of f of zn times the modulus of delta z. But now we can put that back together into an integral, and the integral that it goes back to is this one right here. So this is going to be the integral over gamma of f of z in modulus and dz in modulus. But now notice that if we in addition, I should say, assume that inequality up there with the modulus of f, this is going to be less than or equal to m times the integral over gamma of the modulus of dz. But the integral over gamma of the modulus of dz gives us exactly the arc length, and that is L. So this is equal to mL. Okay, and so that completes the proof of this theorem. Now we're going to do a couple more results. So for our next result, we'll show that an analytic function f has a primitive on a domain D if and only if the integral over gamma of f of z dz is equal to 0 for every closed gamma in D, so every closed curve. Okay, so let's do this forward direction. So let's put a little picture of what's going on here first. So let's say this is my complex plane, and let's say this is my domain D, and then inside of that, I have a closed curve, and this is my closed curve gamma. But now let's calculate our integral over gamma. So our integral over gamma of f of z dz, well, that's going to be the integral from any point in gamma to the same point. So let's say this point here is alpha, and then integrating over this whole curve means that we are starting at alpha and ending at alpha. So that means we can write this as the integral from alpha to alpha of f of z dz. But now we can apply the fundamental theorem of calculus for analytic functions. So it has a primitive, so we can take that primitive and evaluate it at the endpoints. So let's say its primitive is capital F. We have this as f of alpha minus f of alpha, which is equal to 0. But that's exactly what we needed to show to prove this forward direction. So this forward direction is quite short. Okay, so now let's prove this reverse direction, but we're going to need a bit more room, so let's get rid of this. So now we're ready for the reverse direction. And before we get started, let's notice that if we've got an integral which is 0 over every closed curve, that's the same thing as it being path independent. So that's something that you do in like a multivariable calculus class. Okay, so now we'd like to define something which looks like it would be the primitive for capital F, and then check that it actually is the primitive. So let's take any number, I'll call it z0, which is in D, and then let's define capital F of z to be equal to the integral from z0 up to z of little f evaluated at w dw. So now we would expect the derivative of capital F to be little f if in fact we were within real variables, because this is like how you define some sort of abstract antiderivative in real variable calculus. So we want to make sure that this works in our complex analytic setup as well. So let's notice that we want this thing to be analytic, which is a little bit stronger of a condition than being differentiable. And in fact, what we'll want is that this sort of condition over here holds for capital F. Remember, it has to satisfy the Cauchy-Riemann equations. So let's write that over here. So here's what we want to show that will finish all of this off. So we want to show that f prime of z is the same thing as the partial of f with respect to x, which is the same thing as 1 over I times the partial of f with respect to y. So that will show that capital F is analytic. Okay. So let's get to that. So we'll first take the partial of f with respect to x. So partial of f with respect to x. So let's recall that that's going to be the limit as delta x goes to 0 of, let's maybe write it as f evaluated at z plus delta x, where we're keeping in mind that delta x is real, minus f of z over delta x. But now let's use the definition of capital F to rewrite this as the limit as delta x goes to 0 of, let's see, I'll take this 1 over delta x out front, and then we'll have the integral from z naught up to z naught z plus delta x of little f of w dw, and then minus the integral from z naught up to just z of f of w dw. But now let's notice that we can smash these together, and that leaves us with the limit as delta x goes to 0 of 1 over delta x, and then we'll have the integral from, this will go from z up to z plus delta x of f of w dw. But now notice that's just parametrizing a horizontal line segment from z to z plus delta x. So let's draw a little picture of what's going on right here. So let's say we've got the point z right here, and then z plus delta x, like I said, will be a horizontal line segment. And so we can parameterize it just as this horizontal line segment. And so that'll in fact be maybe parameterized as gamma of t equals t, where t goes between 0 and delta x. That would maybe be a standard way of doing it. But now we can rewrite this integral using the parameterization of that line segment, and that gives us the limit as delta x goes to 0. We have 1 over delta x, and then we'll have the integral from, let's see, it'll go from 0 to delta x now of a f evaluated at this parameterization. But notice the y part isn't changing, only the x part is changing because it's a horizontal line. And so let's maybe expand f into its real and imaginary parts like this over here. So this will be u evaluated at x plus t comma y plus I v evaluated at x plus t comma y. And then we'll have dt here. But now we can see that this is essentially set up for the second fundamental theorem of calculus for real valued functions. And so the integral and the derivative will take care of each other. And this will leave us with u plus iv, which is just f of z. So let's notice we started with the partial of f with respect to x, and we ended with f of z. But recall, we want a primitive for little f, so we want this like derivative with respect to x to be equal to f prime, but f prime should be equal to f of z, this little f of z. So that means we've got one last thing to check, and that would be that this guy right here, this 1 over I times the partial of f with respect to y is the same thing as f prime, which is f of z, this little f of z. But I'm actually going to leave that for you guys as a warm-up exercise because it follows almost exactly like this. So we've got one more result, and then, like I said, I'll leave you with some warm-up exercises. So now we're ready for one more result, which is called Cauchy's theorem. So let's start with a bounded domain D and an analytic function f on D that extends smoothly to the boundary of D. Then the integral over the boundary of D of f of z dz is equal to 0. Okay, so this is actually going to go pretty quickly, again, using methods from multivariable calculus. So let's see how this goes. We've got the integral over the boundary of D of f of z dz is the same thing as the integral over the boundary of z of u plus iv, and then dx plus I dy. So we've decomposed f into its real and imaginary part and dz into its real and imaginary part. Okay, so now let's multiply this together. So this is going to be the integral over d, or the boundary of d of u plus iv dx. And then it'll be plus, let's see, iu minus v dy. So that's what we get if we decompose it into its dx and dy components. But that looks an awful lot like an integral that we could calculate with Green's theorem, so let's do that exactly. So by Green's theorem, that'll be the double integral over d of the partial of this with respect to x minus the partial of this with respect to y. So that's going to be equal to I partial u with respect to x minus dv dx. And then we'll have minus partial u with respect to y minus I times the partial of v with respect to y dA, because now that's a double integral. Okay, so just to reiterate, that was the partial of this with respect to x minus the partial of this with respect to y by Green's theorem. But now we can start canceling some stuff because we know that f is analytic, so it satisfies the Cauchy-Riemann equations. So this partial v with respect to x will cancel this partial u with respect to y because they have the same sign, but by this part of the Cauchy-Riemann equations. And then furthermore, this partial of u with respect to x will cancel this partial of v with respect to y. So those cancel as well, leaving us with 0, which is exactly what we wanted to end up with. Okay, so let's get rid of this and then I'll leave you with some warm-ups. I have 4 warm-up problems to leave you with. So the first is to finish the proof of the analytic primitive. So that involves finding this partial of capital F with respect to y and showing that this is equal to little f of z as needed. Then the second, consider gamma, which is this closed triangular curve. So it goes from origin to the number 1 to 1 plus I back to the origin. And then calculate the following 2 integrals. So the integral over gamma of the real part of z dz and the integral over gamma of z bar dz. Then next is to show that the integral over the circle z minus z naught equals r of z minus z naught to the m dz is equal to 2 pi I if m is equal to -1 and 0 otherwise. So you can do this by parametrizing this z minus z naught equals r pretty easily. So this is pretty similar to the one that we did where we just looked at the unit circle. Then finally, show that the modulus of this integral is less than 2 pi times e squared. And that's a good place to stop.